So, good morning, all participants. Welcome for today, session 10, and the title was Energy Storage Material for Renewable Energy Applications, and eminent personality of Dr. M.V.Reddy, Institute of Research, Hydrocubic Electrician and Energy Storage, Canada. Warm welcome, sir, for our Renewable Energy for Industrial Domestic Application 5-day online program and sponsored by ACT Training and Learning Academy, FTP. And my colleague will give the introduction about the resource person. Over to Pawan, please.
Thank you, M.V.Reddy, sir. Dear participant, good morning to everyone, one and all. So it's a great pleasure for me to introduce our speaker today, who is going to talk to us about the energy storage materials for renewable energy and energy applications. He is none other than Mogahali Venkataswamy Reddy, simply Dr. M.V.Reddy, currently working as a senior researcher at Institute of Research Hydrocubic Center of Excellence in Transform Electrification and Energy Storage, Hydrocubic, Canada. A warm welcome to you, sir, to this wonderful session.
Thank you.
Dr. M.V.Reddy obtained his PhD in the year 2003 in the area of material science from the University of Bordeaux. Dr. Reddy, sir, worked at National University of Singapore during 2003 to 2019. Our speaker, although having spent almost 20 years of a career for developing a new lithium-ion battery materials. Also, Dr. Reddy has published more than 200 papers in various reputed international journals. Sir also obtained an H-index of 66 with over 15,650 citations. And also, Dr. Reddy, sir, is serving as an editorial advisory board member in a material research bulletin and Journal of Energy Storage elsewhere. Dr. Reddy, sir, has received many prestigious awards in various national and international conferences. Recently, sir received Battery Materials Award from the ESI IISc Bangalore. We are very much thankful to you, sir, on behalf of Department of Mechanical Engineering, JNTUA College of Engineering, Pulivendula. Thank you, sir.
So once again, thank you, Chairman, for your kind introduction and invitation. So whatever, my voice is audible, sir?
Yes, sir. Yes, sir.
Okay. So once again, thank you, Dr. M.V.Reddy garu, for his kind invitation, as well as organizing the excellent workshop on the renewable energy material. So today I'm going to focus on energy storage materials, for especially for renewable energy applications. So I've seen the program. So based on the previous speaker, I think people will already have been caught the different speakers with various personalities. As you can see clearly, I think people have covered with the different areas of energy, like renewable energy, hydrogen, and then fuel cells, or something like solar cell, or something, some materials related to, I think, future going into the photovoltaics, or something like CO2 capture, or some other type of the all type of renewable technology we're going to listen. So today I'm going to mainly focusing mainly on lithium batteries, so some fundamental in terms of I think related to the both the mechanical and electrical engineering point of view more, and still some slides are useful for in terms of the both people are working with science and engineering background. So presently we are based in here Canada, where the Quebec, both French, English and French speaking colony. And also in addition to this one, we can see especially something like January, February, some extreme climate, especially temperature. It may go to sometimes may go to 30, 40, few days, etc. In addition, we can see some other beautiful climate changes we can see. So this is my outline of my presentation. Today I'm going to introduce the topic, just a different type of the some general introduction, followed by something in how the battery material, how to calculate, and something little more fundamental, and few examples related to the and which are the promising material for EVs or grid storage, and what are the real challenges in terms of energy storage or power density, etc. So I think what I am mentioning that research is like suppose I know that many people are coming from rural different type of colleges. I think so. What I am telling that we have facilities with proper equipment. I think we can do. Think starting not only graduate or masters, including I think some demonstrate already. We have been demonstrated some example with high school and junior college students in Singapore. So what I am mentioning that so since like places like Singapore is a small country within 40-kilometer radius, anybody can access and then visit the lab, and then at least they can do 1 year part-time research in the area of energy storage materials, etc. So these are the small contribution. I think with depending on different programs, I think they're able to contribute not only some research projects as well as some few papers we've been published in some international journals. So, and few students are able to they're able to present their talks in the in Singapore Science and Engineering Fair, as well as something like some other prestigious conference with the national level. And few students are able to presented their talks in the Intel International Science and Engineering Fair, and also other parts of the world, including the Europe as well as Japan, etc. So, so these are the small group within Singapore, as well as some few students with various parts of India. So they visited our lab, and so many students have been nearly 4 to 5 giant PhD students have been trained in the Singapore for the last 16 years. So again, I'm mentioning few students from other part of the world, including Iran, and some people from UK, etc. So these are my small collaboration within Singapore, as well as various part of like India, as well as I can see. Although I work with sometimes mechanical engineering and chemical engineering and other part of the engineering domains within the faculty of engineering at National University of Singapore. So these are my small, although my interest was in new materials for lithium, and or if you talk about sodium, all type of things you can do. And since principle is same, only just you replace the material by the oxides, etc. Either you can do counter electrode, you can do all type of the batteries. So I'm going to tell that which technology is really good and what is why this lithium is more popular. So when compared to the other technology, I'm going to explain in the coming slides. And due to time limitation, I'm not able to discuss all the other type of technology or something like energy storage. And also, we were small work I did with the dye-sensitized solar cells in collaboration with the mechanical engineering department in US. So also, since my background was a thin film micro batteries, I think some of the work we did with some electrochromics, and especially some recently some of the work we contributed in the area of electrochemical, for example, in situ in situ structural studies, for example, to try to understand how the batteries, what is going to happening with respect to during charge discharge, or sometimes in terms of structures, or for example thermal management, etc. So now materials are broadly classified as, you know, that all people are familiar how the human history and prosperity started from Stone Age, Copper Age, Iron Age, Rubber Age. Especially Silicon Age made them to think in a different way. So that, for example, discover vacuum tubes, computers, or something like iPhones. So again, the composite age, especially mechanical engineers during this time, I think people have been developed with lightweight materials, especially superalloys. So that will be very useful. Suppose, for example, you see the casing of your iPhone or a desktop, they need lightweight material. Again, the composite material will play an important role. Again, the two around functional material age, what they call as nanotechnology, around year 2000, and now the molecular age. And future, always people are talking about the any intelligent materials, irrespective any area, either due to the energy, environment, healthcare, or including that our mechanical engineering. Always people call as each area they have something like where people are looking for intelligent material. And in terms of other things, the low carbon age material, especially always you to look for example, CO2 capture or to reduce the CO2 pollution, for example, using the electric vehicles. These are the people or materials are going to talk. So already I mentioned the importance of the energy, water, healthcare, and then water technology. Again, as a researcher point of view, that maintaining sustainable environment and healthy lifestyle and waste management, reduce the air pollution, infrastructure for any smart city development, etc. Again, the materials are broadly classified based on the, for example, building materials, phase change materials, and for example, wood, sand. So again, remember that construction material will vary depending on the region to region. Again, the so we have to plan accordingly. Electronic materials and energetic material, especially engineering material, if we talk about iron, steel, and superalloys, and especially in terms of food and pharmaceutical industry. Based on physical properties, we broadly classify metals, semiconductors, and insulators. Again, we broadly classify on magnetic, optical, and dielectric, and radioactive and thermoelectric materials. I think today I'm going to focus on mainly on the energy storage materials, especially people. These are very important. Presently, I think people are looking for the promising materials for electric vehicles as a smart grid, etc. So again, the impact, for example, impact of steel for the transportation technology, or if you talk about the lightweight aluminum or the alloys, so we can use it for the aerospace, or if you talk about the composite metal, for example, carbon fibers, etc., we can use it for the aerospace applications. Another area is optical material. For example, people are talking about the smart windows or electrochromic windows. I think that, and also if you use it for different type of the, like for example, fiber lasers and then mirrors, etc. Or sometimes people call it the metamaterials, etc. We can use it for the different type of the application. Again, I'm telling this more focus on the more on physics related research. So in general, research is needed for smart material. If you talk about the building, or if you talk about the light saving, or if you talk about the smart glass, transparent plastic materials, or if you talk about advanced flexible organic material for photovoltaics, I think resistive switching memory application, for example, if you talk about the electrical engineers. So sensor technology, I think people are talking about always lidar type sensors are very expensive. Suppose these sensors are using for the autonomous electric vehicles. So that's why I think the cost of these lidar sensor should be to be reduced. And materials for graphene, CNT, especially for smart cities. And I think always we are facing a problem with, now we know that we have some problem with the internet, for example, including remote, or everybody want to fast internet connection. Again, I think we are looking for the 5G, 6G terahertz electronics, means smart materials. And again, the smart materials for smart grid, electric vehicles, autonomous vehicles, etc. And so, for example, I think previously some people have already solar cells, people have been already talked about the chargers, including EV, or for example, so you want to grid storage, etc., etc. So again, these are all the different type of hot areas. These are few examples. Again, I'm mentioning that since it's focusing on the energy storage, I'm talking about some few examples related to this one. In general, applications, I think we can use it for the materials, we can use it for energy, environment, and healthcare, and different type of the applications we can use. So now I think the importance of nanotechnology again, so we can use it for the different type of applications, starting from the pharmaceutical and different type of the energy and environmental applications. So now I think anyway, this is the world data. Still the publication keep on rising these particular areas. So now I'm going to mention the introduction. So always people are talking about the, to solve present environmental problem. Always people are talking about green renewable energy technology. Among them, I think the available is the solar, since we have the good solar energy, and hydro. Maybe places like here, I think there is a lot of water that I think they can produce hydroelectricity. And batteries, I think that people are already, there's a very common lithium batteries, means people are thinking about using the electric vehicles, especially for big cities. I think to reduce the pollution, people are thinking about the electric vehicles is a little bit alternative for to reduce the, and also you know that presently they keep on the oil prices keep on rising. That's why always people are thinking about the batteries are the future, maybe by 2050, many things are going to happen in this particular areas. Again, other alternative include, I think people are talking about bioenergy, fuel energy, hydrogen storage, and catalytic water splitting, wind, mechanical, nuclear. These are the different type of the technology has been worked by. I think there are some all limitations are there in terms of cost and efficiency. There are all the problems are there irrespective of the any type of the technology. Again, in general, energy storage, for example, renewable technology or environmental engineering is interdisciplinary area. Sometimes we need some expertise in science, and sometimes engineering also. Again, engineering is a very vast. If we talk about material engineering, production, or chemical, suppose you want to prepare large scale materials, we need the chemical engineers. Mechanical engineer is very important, so that sometimes you want to integrate your battery into the your engine. Again, you have to work together. Or if you civil is also very important. Or sometimes you talk about the autonomous vehicles, even a good infrastructure. Again, civil engineering also we have to talk together. Again, electronic engineer, automobile engineering. Again, this is very important. Sometimes you want to be sensor management, electrical or electronic engineering will play an important role. Again, at the end, I think we need the management science. So that is very important. You have to manage all the, we need the, so in general, it is a multidisciplinary, interdisciplinary area of science and engineering. So what I'm mentioning that depending on expertise, I think people will focus on the particular areas. So I'm always as a material researcher point of view, I think always people are talking about high energy density or power density. For that case, I think novel material development is very important. Or if you're looking for, sometimes people are looking for sometimes synthesis or try to understand what is the real problem for this material performance is going to be degrading. Those are all things as a researcher we have to start. Again, as an industry, their job is to look for the large scale preparation and then look, and then so at least with existing material they will look into the, and finally they would like to make a profit, and then so there's a way it will going to work with the system. So importance of energy storage, suppose for example, if you talk about this smart distribution or batteries, or if you want to use solar energy or wind energy, or if you want to turn with industrial applications or the smart buildings, so I think there we have to use this battery or with and at the end another is the electric vehicles. I think we want to use this batteries, we can use it for the smart infrastructure. So as you see that clearly that, for example, energy crisis, the old data keep on, the prices keep on increasing. Especially here, you can see that this is the world, still the prices keep on rising. And also advantage of use of electric vehicles, I think we can reduce the CO2, CO2 emission reduction. So what I am mentioning that depending on the, if you talk about the smart grid, we need in a megawatt range, and electric vehicles, plug-in electric vehicles, I think we need something like less than 100 kilowatt. Some portable application is 100 watt hour. So again, so for example, the small devices, we need something like, although materials are same. So if you go for smart bigger devices, I think the mainly we need large materials. Again, the cost is also major factor. So if you want to use this type of material, so again, the use of the advantage of this, if you can replace the gasoline vehicle by electric vehicles, I think we can reduce the further reduction in the air pollution. Another important is, I think, solar energy. I think people have already been talking about the previous speaker. I think the main issue is that in terms of the, I think we can reduce further cost by using the, I think if we want to store the solar energy, we need a battery pack. Again, battery pack is a little bit more expensive, so that's why. So we have to look for the materials should be high energy density and long lasting, and cost should be lower. So that's a little bit interesting things. It means that we need something like low cost battery pack is needed for the to store the solar energy. So another important area, for example, battery operated autonomous electric vehicles. Again, it will uses the self-driving cars with uses artificial intelligence, lidar, and radar sensing technology. So, and major benefits of these autonomous vehicles, we can reduce further, lowering the fuel consumption, as well as we can reduce the CO2 emission, as well as we can reduce the traffic consumption. So that, I think these are the very important things. Always people are talking about the smart city development. So I think these are the almost like 7 trillion annual revenue by 2050. And also another thing is that people have predicted almost like 90% of reduction in the vehicular crashes we can reduce by using this type of the autonomous electric vehicles. So the typical autonomous electric vehicles, again, it seems to be the lidar sensors or videos, and there is a computer, and there is a GPS system. So again, since it will clearly show that, so it is the importance of, for example, mechanical engineers or automobile engineering, and then again, we have to work with the electrical engineer, and then we sometimes we may need some computer engineer, just programming all this one. You have to. So again, apart from the material development, that's why at least scientists all together we have to work together in a large scale. For example, in industry, that is the way it's going to work. So these are the different type of companies investing with this type of autonomous and electric vehicle. So as you can see clearly, so especially something like Tesla, these are the very important, I think, main contributor for especially electric EV market, etc. So now I'm going to mention that I think all people are familiar with how the mobile phones looks like. For example, you see this particular type of pouch cell. I think all people are using this type of batteries. I think we may use something like pouch cell. So, and I think people are familiar. If you open your laptop, you may use something like 18650 cylindrical cells. So it looks like that depending on the energy required, they can put it. So future, if you would like to run with the electric vehicles, they can use this type of 18650 cells, put it in a what they call a different in a module, and put together, and we can make a big type of pack. So again, for example, so almost like if you want like the electric vehicles, in nearly 7,000 cells, if these 18650 cells are putting together to run that cells, to run your electric vehicle. That's why if you want, again, if you took too many cells, again, the battery management, or if you talk about the, for example, thermal management, there are all the things you have to take into consideration. So in summary, so if you use the materials for electric vehicles or grid storage or in any other type, for example, home or any other type of applications, again, the materials are same. Again, the technology or the fabrication or design will be different depending on the which type of the depending on which type, depending on the applications. So this is one general slide. I think people are, for example, the Tesla model. So as I mentioned, the 18650 means 18 mm diameter, and length is 65 mm cell. So again, the battery pack, for example, 85 kilowatt hour, and this is like I'm going to tell what is meaning. NCA means what type of cathode materials are going to use, and cell is 3.2 amp hours. Nearly almost like 7,100 cells are going to put. That's why it's very important. With too many cells, I think the battery management. Again, people are talking about battery weight is almost like 540 kg. So although your material weight is like real lithium batteries weight is a little bit lower, again, if you talk about the casing and due to safety, all this one, the weight of the your battery pack is going to be more. Not the material is related to other things, for example, stainless steel and then current collector, etc. So what type of the, for example, if you talk about the electric smart materials for electric vehicles or grid applications, I think always people, if you talk of any smart batteries, we have to look for high energy density and power density. I'm going to explain how to calculate high energy density and power density of any like any battery or any type of battery. And these very important points, again, you have to look for high capacity and lightweight, etc. So again, it is very important long cycle life. I think we have to once when we purchase the battery, and then we need whatever the promised like year they mentioned 20 years or 30 years, whatever the year they mentioned it has to work. And more thing is the reliability, in the sense that once you if you mention something like 360 kilometer per bus, one particular charge is to work. So that's why sometimes they've tested in the depending on the road conditions. So that's why, for example, place like in remote place like India, so depending on road conditions, you may your driving pattern is going to vary. Again, it has to adapt the climate conditions. For example, minus sometimes it may go to extreme temperature like minus 40 degree, or sometimes you may go to 60 to 70. It means that so that's why this battery management software it will do is that sometimes with low temperature it will tell that you're just doing some additional heating, or if it is go to high temperature it may to go to the cool the things. The reason is that since we use some electrolytes, So if you go to low temperature and negative to low temperature, again the conductivity is going to be reducing. So sometimes you may not. So that's why we need some optimum conductivity we get by using only the depending on the temperature. So Coulombic efficiency is nothing but I'm going to explain in the next slide how to. So usually around 99% to 98% is really good. And impedance of the cell is nothing but a resistance of the cell. So usual way is that without opening any batteries, for example, it will tell that life cycle of the battery, if it is good or bad, or sometimes we may get some particular resistance before charging. After long-term cycling, your resistance is changing. For example, 10 ohms change to the 1000 ohms within 1 year or 6 months. Then it clearly indicates something is going to happen to your battery. Something is degrading either due to electrolyte problem or due to material issue or something like other technology, etc. So this is very useful tool to understand this impedance technique is very useful. And always people are talking about fast charging. So in the sense that, for example, like filling the gasoline, is there any way to charge a battery within 1 minute, 2 minutes is a question mark. So they may, based on our experience, it means usually because these are the solid state way oxides. So there is a diffusion problem. That's why sometimes you have to wait for some time to slowly lithium is coming in and coming out. So it's still use of the nanotechnology, and then recently there is a lot of interesting things going on. These fabrication technologies, something like current coating, or something like current collector design, or different ways. People have been still a lot of interesting things is happening with respect to fast chargers. In addition to the fast charging developed by the electrical engineers. So again, at the end of industry, what they're looking is that more safer material, low cost, and no toxicity. I think these are the three important factors you to look into the consider. Maybe it applies to this same thing like to solar cells also. Again, so as a battery, I think sometimes we may have problem with the cost, and some cases we may have a problem with the safety. And after doing all this one, we look for sustainability. It means that whatever the things you do, you to use this one for the recycling is very important. So now I think people may ask you that, okay, who is the champions? For example, they will tell, okay, so sometimes India, it is very difficult. It depends. So actually, you know that any lithium battery manufacturing, we need something like raw material. I think we need a lithium source because since we can use it for electrolyte and cathode, and these are the elements we need it. Since you have people have this type of mineral and mining, so they have particular this type of minerals are that it is easier for them to those people. And another side is negative side is the anode. They need a graphite mines and the current collector like copper, aluminum, steel for cell manufacturing, and especially neodymium and dysprosium. So these are the permanent magnets are using for the electric motors. So that's why. So this type of the all raw materials they have, those are a little bit more. They're more going to be more dominating with. That's why sometimes So that's why people are fighting with depending on which are the. For example, lithium carbonate is in Afghanistan recently, and with other part of the world, especially lithium is a little bit. That's why abundance of lithium is a little bit low. Still, I think people are concentrating with existing lithium mining and then trying to understand which type of materials are promising for the applications. And again, we do electrochemical production, manufacturing, end use, and recycling. I think that is the way it applies to the raw. Sometimes people are talking about the cost. I think cathodes, depending on the cathode, also is very expensive. If you talk about the anode side, graphite, since graphite mining, so graphite is less expensive when compared. And again, electrolyte separator, all this one is the cost will coming from the different part of the, for example, copper foil, aluminum foil, electrolyte, etc. So now I'm going to introduce the, for example, what I discussed, what is there inside the battery. So all people are familiar. So once you buy any batteries or any type of small pouch cell or anything, you may see something like positive terminal and negative terminal. Usually positive terminal, if you talk about lithium ion battery, either they have something like NCA, means lithium nickel, like aluminum oxide like NCA, or NCM like lithium nickel cobalt manganese oxide, layer type oxide they used. And sometimes like LFP, means lithium iron phosphate, is also another type of the batteries, since may get slightly lower energy density. Again, since phosphate is like phosphor oxygen bond is stable, and that's why this is more little bit good thermal stability. And cost wise is, since iron is there, cost is a little bit lower when compared to the lithium, nickel, cobalt oxide based batteries. So again, so this type of cathodes, if you take any metal oxides, you mix with a binder and a conducting carbon, and finally coat it on the aluminum foil. The reason we are using aluminum foil, because aluminum is going to stable up to 5 volts. And suppose, for example, if you use another side, the negative electrode, we use a copper foil. If suppose if you use the copper foil to this side, so copper will oxidize above 3.5. So that sometimes, due to C, that's why we have to use the current collector in an appropriate way. Separator is very important. So it is like a polymer separator to avoid this short circuit. Only lithium ion will be, for example, since we're using electrolyte in between, so the lithium ions will move out and come back. So that's why, so separator will play an important role. Sometimes people are talking about the, sometimes we got high temperature, there is shrinkage of the separator, or something like lithium dendrite growth, the short circuiting occurs. So that's why separator should be, so will play an important role. Yes, so I'm going to explain what type of the characteristics of the good separators. So suppose some people are talking about the sodium batteries or potassium batteries, just only replaced by, if it is sodium containing oxides, you call sodium containing the cathode, and you can take the sodium, you call sodium ion battery, or potassium, or sometimes you call it zinc oxide, zinc, magnesium, and then, so the problem is if you go for divalent, since because of mobility issues, sometimes you may not get what is expected energy density and potential also. As of now, is more popular is lithium, because so almost like the voltage is stabilized, and this material is a little bit more stable. Once you prepare this material, they're more stable. So again, the charge we call as oxidation, sometimes called anodic scan, and sometimes we call it positive current. Sometimes electrical engineers we call it the state of charge, or sometimes the DOC means state of discharge, etc. Discharge we call it the reduction, cathodic scan, and negative current. These are a little bit fundamental terms I'm going to adapt in the next coming slides. Electrolyte, we use something like a 1 molar LiPF6 It is like inorganic lithium hexafluorophosphate. Advantage of this particular electrolyte, conductivity is really good. And then you may see that use of advantage of the organic electrolyte is you can go up to 5 volts. Suppose if you use aqueous based system, again, maximum is 1.35 or 25 volts you can go. That's why always people they use with something like organic electrolyte. We use it for, and so now ionic liquid, and sometimes polymer electrolyte and solid electrolyte we can use. Current collector, I already mentioned copper and aluminum foil. So copper for the anodes, aluminum for the cathodes. And binder we use, usually we use a polymer PVDF as a binder. Sometimes people use CMC, means carboxymethyl cellulose. So most commonly PVDF is a very commercially used binder. And sometimes we use to increase the conducting super P carbon to improve the electronic conductivity. And so, for example, we want to fast charging, etc. We can use super P carbon. So again, I think these are typical cell. Whatever the way, if you talk about the grid storage, again, the main components are same. Only thing is depending on the energy requirement, they will put it depending on the shape and size will be different. And then vertical fabrication technology, or it will vary depending on the which type of application, depending on the applications. So now I think 2019 Nobel Prize is given to the well-known chemist. This is one of the almost like 19. This year is 99 years. One of the oldest Nobel Prize winner, got the Professor John Goodenough, both physicist and chemist. His contribution on the layered cathode. That's why nowadays all our mobile phones are using this type of this discovery made them to use it for the advancement of the lithium-ion battery for the portable applications. In addition to this one, I think Michel Armand, French chemist, will play an important role in developing of the, for example, rocking chair and polymer electrolyte, etc. So I think people are talking about the, I think nowadays some people are talking about the sodium batteries. Again, sodium battery is also very known, because since the previous institution where I did with PhD in France, so almost like 1973 already these compounds are known. Only at the time people are studying with both fundamental studies. So the problem with this type of sodium compound is a little bit potential we cannot get as expected when compared to lithium based system. And these materials are a little bit hygroscopic, and then sometimes handling with the sodium is not so easy when compared to the for example lithium or graphite, because another side is graphite is known, so that's why easier for us to in terms of the in order to make a full cell. If you can use a lithium based system with lithium, graphite is one side, and layer type cathodes are different type of cathodes, we can use it for the anode side. So again, now I'm going to spend more detail. I think what is how the principle of the batteries. So it contains, I already mentioned the cathode, anode, and then the separator. So during charge, lithium move from the from this side to from the cathode to anode, where electron will pass to the external circuit. During discharge, again we'll go back, lithium will go back to the origins. That's why we call it the rechargeable batteries. Okay, so idea is that if you don't go with this, lithium will not go back to the original state. That's why we call it irreversible or non-rechargeable batteries. So is typically this what they call schematic diagram. So if you plot with the current versus potential plots, once you remove lithium from the structures, it is for example lithium cobalt oxide. So lithium is 1 minus X means cobalt 3 to 4 plus. That's why we can develop a potential. For example, this is very important. We have to get nearly 3.10 volts. This is a positive current and then a negative current. So if it is rechargeable means you have to get a positive and negative. That's why we call as a rechargeable battery. So it is very important if any materials use always or any new material, you have to get a positive current and negative current. And so this is very important. So this is called as a potential static plot. So the same, for example, this same type of this lithium cobalt oxide I plotted in the voltage versus capacity means a constant current. See what we notice around like 3.9 volts, we are able to see it like this type of plot. So voltage of the cell is nothing but, for example, this charge minus, for example, 3 point minus 0.25. So this is the voltage of the cell. If you calculate the energy density, the voltage multiplied by capacity, whatever the value you are getting, and we can calculate. So the major challenge is that people want to be reduce the number of cell in your electric vehicles, or for example, if you want to use your mobile phones. Yeah. So people want to be long time or want to use it for more time. I think we will now major challenge is that we have to extend the new materials, or whatever the materials we use, we have to get the extended platform in slight higher charge potential. Instead of getting something like 200, we go to 400, 500. I think that really breakthrough research, and so that will be very useful for the future energy storage application. So that's why discovery of the new materials are looking for existing, the improvement of the materials is needed for the large scale future applications are needed. Okay. So now I think these are the different type of mechanisms. Since you are mechanical or engineering background, don't worry about this like different type of. So the practically, for example, your graphite or your cathode anode usually will undergoes intercalation deintercalation reaction. Means that so one lithium or two lithium, it will go inside the structure and coming back. So we don't see any structural modifications. That is very important for the future applications. For example, if you use silicon and tin, so it may see some volume variation. So we can see reduction as well as the volume variation. The problem is that, so depending on the materials, sometimes you may see the capacity fading. We can see that's why in this particular technology, I think always people are looking for either something like a nano size. We can reduce the particle size, or something like carbon coating or carbon composites. People can use it for again. So again, advantage is that although we can get slightly higher capacity when compared to a graphite 330, you may go to, for example, silicon use I think around 3000 or something like it will go. So again, conversion type of the oxides, again, there is a lot of interesting oxides and alloy based system. So all the different type of materials are there, so you don't need to worry too much. So still, as a which are the commercial materials, what type of mechanism means is like intercalation, deintercalation. So I think this is very important if you are either any background, either any type of engineering, mechanical or any either science. So if you want to write your publications, always you have to write it in a proper mechanism. That will be very useful. So that is the way. So at the end, people are going to accept your papers. So for example, I think any engineers or any scientist, if you want to do battery materials, always people are looking, if it is good materials, it means you have to look for the low atomic weight. It's what are the formula, if you calculate the formula weight or atomic weight, it should be low is good, so that theoretical capacity is nothing but number of lithium into Faraday's constant by molecular weight of any material. It will give the milliamp hour per gram. So always, since the denominator, so always look for the low atomic weight, then automatically we can go to higher theoretical capacity. Ideal anode material should is to show lower discharge, lower operating voltage. For example, I told you the anode means something like graphite, around 0.25, like that way. So if you three type, for example, lithium iron phosphate, around you are getting around 3.5 volts or 3.9 volts in case of lithium cobalt oxide or some other type of the oxides. We can get higher voltage. So in summary, already I mentioned that voltage of the cell is nothing but average potential of the cathode, means this is the one, minus anode materials. So finally we can get something like, so suppose you want to be high energy density, what energy density is nothing but voltage of cell multiplied by capacity, like. So usually I think the major now main issue is that whatever the way you research still, so this external plateau is something like limited, so that's why the new research you need to look for the law, something like innovative materials, test to work with high energy density applications. Again, another important point is that cathode anode must not soluble with a solvent, in the sense that if you use this type of system, it will not soluble. So this is a very important point. And another important point you have to consider is the cathode anode must not first. It means that we need something like good. People are talking about the fast charging. So there, I think we have to look for the mixed line conductor. Sometimes what people will do is that to improve further, I think they use something like nanostructuring or something coating the particles by using something like nano coating or carbon coating with ALD. Some of the fancy techniques are going to use. So these are the things already demonstrated with a large scale systems, for example, cathodes, cathode material, etc. So in summary, so due to the high, for example, volumetric as grammetric, so that's why lithium batteries are really good. And as I mentioned that, so in terms of voltage wise, it's slightly higher when compared to other things, and lightweight. So because of this one, we can use it for the space as well as a, for example, different type of the aerial vehicles, autonomous vehicle, etc. So another point, since the more fundamental, again, the electrolytes are also very important points. So electrolytes also, for example, if you want to use electrolyte, usually either you can use liquid electrolyte, for example, inorganic based salt, lithium. If it is lithium based chemistry, you can use lithium containing salt. If you talk about sodium batteries, you can use the sodium fluorofluorate or sodium containing salt or potassium, etc. If you talk about zinc air or zinc or magnesium, all this one you need a respective salts are needed to, so make sure that, so more popular is lithium because of the, we know that lithium is a smaller ionic radius when compared to the potassium, sodium. So advantage of this lithium based electrolyte, for example, this particular electrolyte lithium hexylboron phosphate, is that conductivity is reasonably good, and some limitations are leakage and sealing and flammability issues. And so that's why people have been looking into the polymer based electrolyte. So either you can use inorganic electrolyte, either we can use a polymer, or sometimes ionic liquid, or sometimes people they use something like nanomaterials, for example, some pillars, everything they've been used it for to improve the conductivity. Still, I'm telling that to talk on the particular each topic, it took again, I need something like 2 to 3 hours to talk on this particular areas. So quickly, I'm going to, another important point is the separators. So separators are very important factors to avoid short circuit. We can use the separators. Usually, mostly commercially, we use the cell guard separator like polyporous propylene separator. Some cases we may use something like glass fiber. So important characteristic of the separators, we have to look for the thickness is less than 25 micrometer. Porosity is 40%, good high permeability and low electrical resistance, and good tensile strength and good chemical stability, nice wettability and puncture resistance, etc. Again, you can see the safety is a very big issue. That's why other people have realized that sometimes you may see some batteries are going to catch fire, or your laptop is catching fire, or something like a car. So people have there are different reasons. Either the flammability of the electrolyte is one reason, Another is oxygen release from the materials. It means sometimes people they may need the excess than safety limit. Due to the malfunction of the electronic circuit, sometimes there is a safety breaker. Sometimes some particular system it may go to higher than the voltage is being expected at the time. Sometimes you may see the, for example, capacity degradation, or sometimes you may see the oxygen release. That due to repeated cycling, we may see that it may catch fire also. So another important factor is the solid electrolytes. So usually we can use the solid electrolytes. So these are all the, by mixing with, for example, both solid ceramic oxides, both electrolyte and the cathodes mixed together. And here it is very important you to look for the hot press and spark plasma sintering to not to make a good contact. So again, these are the, although it is very easier to tell in reality, so contact is a problem, and sometimes you may be not able to run with, for example, fast charging. So it will be difficulties are still there is a lot of interesting things going on with all worldwide researcher looking for the solid state, all solid state batteries. Again, these are important factors. You look for thermal expansion coefficient as to both things as to match, and good chemical stability. For example, you are going to sinter this materials. If it will not react, for example, cathode electrolyte is reacting, it means that something is interface is a problem. So again, these are the either sulfide based system, because the sulfur containing materials are a little bit hygroscopic. These are not stable. Oxides are seems to be good. Again, in order to make a good sinterability, you need to make a good conductivity. You have to heat the sample. You need something like a good what they call a particle to particle contact is very important. So again, each technology have been something like advantage, disadvantage. So that's why the research is going on again. So use this, for example, this solid state membranes, ceramic membranes, use it for our aqueous electrolyte, for example, to protect the lithium metal, or use redox flow batteries, or people are looking for the what they call the all solid state battery we can use. So now I'm going to spend some time on the material processing and fabrication and characterization techniques. So for example, so it will clearly shows that so whatever the research you do or anything, I think material fabrication or material processing will play an important role. So again, we can play depending on whichever the materials of interest. That's why people are, for example, people are working alloys, accordingly select the alloys, or your lithium batteries, or for example solar cells. I think they may use something like silicon as the best interesting materials. Again, it depends on what type of the research are going. Accordingly, you have to select the particular oxide or particular materials. So again, depending on applications and depending on the properties, and identify the material, understand the structure composition, either by nano and submicron size materials. And again, so depending on that, we need the required processing of the material and application, etc. So it's very important that we can study by nano size. So sometimes people call nano means 1 to 100 nanometer, and submicron size above 100 nanometer is very important. So usually use of the nano size particles, we can, when compared to the submicron size materials, we can, due to the large surface area and shorter diffusion, we can reduce the volume changes, and then that is very important for especially use of this for nano size materials. So these are the, either depending on what type of the materials, depending on fabrication processing techniques, either you can do different type of the particle, either by nanoparticle plates, rods, etc. We can use appropriate or fibers, etc. We can use it. So these are the various material processing. Either you can do chemical methods, or for example, thin films you want to get, you have to go for physical method. So later, as a mechanical engineer, sometimes people they're looking for composites or lightweight alloys. I think for them is whatever the way you do initial preparation, at the end is particle to particle contact or good mechanical properties are very important. So that's why we have to use either by, for example, spark plasma sintering or hard pressing, or I think recently what they call as additive manufacturing, use of the 3D printing. Either sometimes you may use a laser. So different type of techniques we can use. So that's why this is very important, especially this technique is very useful to get the solid oxide fuel cells or all solid state battery, or if you talk about the lightweight alloys or composite materials. So again, so due to time limitation, I'm not able to touch individually all particular methods. Still, I'm able to focus something like few methods that will be useful for the people who are working with the science and engineering background. Again, for example, thin films, you can use RF sputtering, pulse laser deposition, ultra-atomic layer. If you want to be small layer by layer thickness, we can do it. Or you do evaporator or plasma, CVD, etc. And then electrode deposition and 3D printing, etc. We can use it. Especially for thin films, either you can do chemical vapor deposition technique. Again, here we use the reactant gases for thing like volatile precursor we are going to use. And then, so either we can get it in thin films. Again, we can do the atmospheric chemical vapor deposition technique or CVD, etc. Another one is the physical vapor deposition techniques. Again, either you can do here no chemical is involved. For example, you want to prepare a thin films of the silicon oxide or silicon, you can do, or sometimes some other type of the, for example, oxides. So we can try to get. So for example, IC integrated circuits, we need something like ALD, PLD, and molecular beam epitaxy needed. Again, depending on applications, we need optimization of thickness, composition, and then surface and electronic properties are needed. So in summary, I think it is one particular RF sputtering technique. So if we want to play with depending on power and target substitute, we can vary the composition, deposition rate, and understand the, for example, what are the physical and what type of properties are looking. For example, electrochromic people, only for them they have to deposit in the ITO substrate, or for example, your battery, micro battery, you have to use a stainless steel current collector, and accordingly you have to deposit by layer by layer by layer. Or you can do is glass substrate also, just you can use the layer by layer, almost like micro batteries also you can develop using this technique. So regarding the thin films, I think we need something like the expensive technique. For example, nuclear reactions, maybe like RBS, they like helium, a beam is hits on a particular thin films by knowing the backscattering energy. So they'll be, depending on thickness, we can usually that atomic cross section will directly proportional to the atomic number, means higher atomic number will scatter first when compared to the lower one. So based on this particular technique is very useful to know the composition and thickness of the thin films. So I think these are the various techniques, since XRD is a very useful tool to know the composition structures. Sometimes we use thin films we can use. And for example, fast charging, galvanostatic cycling, and conductivity measurements are very useful for the, for example, battery and energy storage which is needed. Or sometimes SCM, TM, these techniques are used to see the morphology or what is going to happening. And at the end, we need something like software to analyze the structures, or for example, to analyze the impedance plots, etc. So again, these are the different type of the technique, for example, in situ cell, Raman studies, and then for example, microscope, SCM, etc. So I think this one particular quickly I'll go through, since X-ray diffraction, I think all people are familiar. So this particular technique is very useful either by any material researcher. So typically we are going to put some sample, either thin films or powder, we try to put it somewhere here. X-ray is coming from the tube, and the incident on a particular thin films or a powder, diffraction will occurs. So by knowing the, for example, interplanar distance and Braggs angle, so we can we can calculate the either your materials is amorphous, or for example is a nano and semi polycrystalline materials. We can see usually if it is a nanocrystalline material, depending on that one, we can see the line broadening. From there we can calculate the average crystallite size. We can tell that your materials is nano size, and we can, depending on the shapes, usually spherical particles are really good. We can compare with what the average crystallite size obtained from the XRD. We can closely match with the TM studies or any other type of the microscopic investigation. So either if your thin films are there, yes, to layer by layer also we can do something glancing angle, thin film XRD. I think this technique will be useful. For example, solar cells, I think people have used this particular technology. So this is one example. If you talk about amorphous, nano, and polycrystalline, the TM images looks like, for example, the simple titanium dioxide. So as you can see, it is like, for example, amorphous materials. So not see if it is nano size, somewhere at 280, we can see this diameter divided by 2, then 1 over d. So finally, if it is a crystalline material, we can get something like dot particle size. So again, these are typical 7-phase crystal systems we're going to use. Accordingly, we have to use it for most commonly, depending on this, most of the materials we've been worked in for the last 15 to 20 years. So these are the For example, people talk about battery tester or fast charger, impedance analyzer. I think these techniques are very useful to for example, how they monitor, for example, uh, fast charging. For if these like a battery charger, what it will do is that it will monitor the voltage. For example, you may tell that some particular lower limit to higher limit, and as a function of time, and fix the current. So that by you can, by knowing the active material, we can calculate the capacity. So sometimes it's very important. This is, we'll get average potentials or etc. It will very useful. Another complementary, so importance of the, for example, you can see that the galvanostatic cycling tests are very useful to calculate the very energy density of the batteries. Already I discussed. So for example, sometimes depending on 1850s energy density, already I discussed about how to calculate voltage into the battery capacity rating due to battery weight. And then power density is nothing but voltage into current, like that way. So accordingly, we can calculate these particular things. And already I mentioned that a step time multiplied by current, and we can calculate the capacity, theoretical capacity. Already I mentioned how to calculate the theoretical capacity of any material. So irreversible capacity is nothing but during the first charge and discharge, you have to get a lower is better. If you do any research, always you get lower ICL is really good. So sometimes too much high ICL, then it may not be interesting. For example, you see some few example, there is something graphene type material. If although you get something 1000, practically it is not really useful, you know. So that's why commercial graphite are really promising, because you may have to get lower irreversible capacity in the first cycle. And capacity fading is nothing but how much, for example, second cycle with the 50th or 100 cycle, whatever number of cycle divided by second cycle multiplied by 100. And Coulombic efficiency difference between the charge minus discharge capacity. So like 100 minus X, we can calculate the Coulombic efficiency. Rate capability is very important. Sometimes, usually that sometimes these are low current rate, higher current rate means 1 C means total energy stored in per day or in 1 hour. 0.1 C means C by 10. So in 10 hours, that's why sometimes they call as C by 10 or C by 5, like that way they will tell you. Sometimes if they wanted to charge a particular thing, they'll tell C by 5 or C by 2 or C by 10, like that way they mention. Accordingly, most commonly they like supplier, they will tell the low current rate, because so that make sure that all the capacity they can recover or they can do that one. So that due to the kinetic problems. Still, you can do higher current rate. Again, the problem is you may not get what are the expected capacity reduction we can see. So that's why we can do something like conducting, carbon coating, etc. You can do. So what are the rate, how to improve the rate capability of the electric vehicles? Because again, either you can do nano structuring of the porous materials, and sometimes you can use some improvement in electronic conductivity of the material, and then electrode design and current collector modification you can do. So again, how to calculate the voltage prediction? You can do either cyclic voltametrograms. So you can tell that, for example, cathodic current, for example, you can see it like something like anodic oxidation and reduction. So depending on this particular like this potential, you can tell that the charge potential and discharge. Again, it is like complementary to what you are getting from the galvanostatic cycling. So again, remember, the 4 volts, 3.97, 3.5. So it will give the, depending on which type of the, what they call as the cathodes. That's why sometimes since come supplier, they will tell that LFP means there the energy density lower, or something NCA, they may get something like 3.97 or 4 volts. Like it. So it depends which type of system, accordingly your energy density is going to vary with respect to, although it is same type of post cell or like particular things, the values are going to vary depending on which type of chemistry they're going to use. I think these are super capacitor. I'm going to quickly skip these details since I don't have much time. Again, you can understand something like both the kinetics, etc. So impedance spectroscopy is a very useful tool. Either you can do, what it will do is that you're going to monitor the high frequency to low frequency. So there, so we can see what is going to happening. For example, resistance going to change during cycle number or voltages, everything we can see. And I think this tool is very useful if you do with the solar cell or any other type of the applications, for example, fuel cell, etc., solid oxide. So these are this particular technique, we can use it for different applications, starting from the ionic conductivity or people want to use it for the solid state ionic sensors or photoelectrochemical cells or solar cells, and for example supercapacitor, etc. So what are the information we can get? We can get the information of electrolyte interfaces, what is going to happen in this one, sometimes diffusion problems, and then something like sometimes we may see the conductivity, etc., depending on the system. So usually I think people are familiar how to calculate the electrical conductivity of the world by knowing the thickness and area, by knowing the resistance, we can calculate the things. And again, I think people want to be dielectric constant, all this one. And these are more on a physicist and chemist, or for example, engineers will do to see how the resistance of the cell, like that way we can do. So is a typical impedance plot of solid electrolyte. You can see there is imaginary plots and real plots. So you can see depending on the system, we may see bulk resistance, grind boundary, and we can separate it, for example, by energy activation. It will give the information about, so conductivity is coming from the grind or grind boundary, everything we can separate it out. So anyway, either you can do two electrode system, as for example, any battery pack directly you can connect it, that is the one way. Or you want to be more fundamental, you can do something like 3 electrode system. Again, the problem is each time how we are going to recording the things are a little bit very complex, and depending on how we are going to do, we have to take into consideration. So what usually I mentioned before doing fabricating, for example, cell, before doing any charge, you will get a semicircle. After going to charge state, you may see some, depending on the 2-3 semicircle, we can see accordingly we have to use something like resistor, capacitor, etc. If it is only one semicircle, only you have to stop somewhere here. Accordingly, depending on systems, it really is very complex. Since I don't have much time to discuss more details still, so this technique is very useful. So without opening any battery, just is going to see the diagnose. So what is going to happen with the interfaces, or there is a problem with the solid electrolyte interface, or something like electrode electrolyte interfaces like charge transfer, everything we can see. Again, it will vary depending on the voltage and cycle number. So, and a lot of things, like for example, here what they call SOC, DOC, state of discharge, state of charge, and with cycle number, etc., we can see get the information. Again, analyzing the data is very complex. So depending on the appropriate electrical circuits are needed to analyze this particular material. So again, these are some examples have been used depending on the system, like different type of the impedance techniques useful, either for example conductivity measurements, or if you want to, this is a particular thing is like solid oxide, for example the scandium yttrium composite, or this is one example if you talk about the dye-sensitized solar cell. Depending on the system, you may get something like usually as a layman's, you have to get lower resistance is really good for the practical applications. So in terms of the key for electric vehicles or hybrid electric vehicle key components, I know that people are familiar with what are the important points. If, for example, you talk about there is a electric vehicles, again there is a motor, and then backside I think they will put it there somewhere battery pack, depending on the somewhere backside they put, depending on the which type of the manufacturing, accordingly they can put it battery pack in appropriate way. So again, we have to understand the power electronics and electrical machines or energy management. Either you can do the battery management or energy storage management is very important. So that's why it is like more an interdisciplinary. I think we need something expertise on the electrical engineering and mechanical automobile. All people have to work in groups. So this is one particular thing, the battery management, BMS. Main challenges is, for example, you have so many cells are there, and there is a sensor. I think sometimes cells must not, for example, in particular cells, it may go to overcharge in individual cell, or one particular cell is over discharge, and sometimes it may not be. Sometimes during charge discharge, some cells it may go too hot, too cold. So those are all things you to. That's why there is a matter. There is a sensor. So that's why there is a lot of interesting things. If you do it, if you work in a large scale battery pack, so these are all the very integration. You need a little bit background in the electrical engineering, etc. So again, battery management, it will detect the, it will tell that at a particular everything should be simultaneously charged, and then sometimes it will tell that if there is any problem with monitor the something like any fault cell, or for example cell balancing or temperature monitoring, or sometimes is there any problem, some particular batteries they have some problem with about the connection, etc. We can tell clearly by using this software. So you can see depending on during charging, so some particular cells voltage is not same. So for example, this is really good. So usually good BMS means is to monitor all the, if you have to, so many cells are there. So you have to monitor the everything should be same way you have to behave. Similarly, discharging the battery, etc. So now I'm going to quickly, since my time is almost 1 minute, just I'll check how much time I have. So now I'm going to discuss about the what type of the almost I finished 1 hour, so that I may take another maybe 25 minutes, 20 minutes, so that at least I can so that so 25 minutes I can try to spend some example on the promising something like cathode and what are the little bit challenges with respect to the materials, etc. So as you can see clearly, this is the voltage versus capacity. So this cathode material is limited, the capacity is limited. So now major challenge is that as a engineers or if you have, people have capabilities, if you want to be high energy density, especially this limit has to, you have to get somewhere here in between that will be. So in terms of anode, there is a lot of example. Still more popular is the graphite because of the lower discharge potential. Some other materials, although we have some capacity, there is some limitations. So we cannot use, and sometimes, for example, silicon, again, although we make it high capacity, there is a cost of it to getting nano silicon. So the process preparing nano silicon, it will take a lot of very expensive and then technology. That's why some people want to be large. Whereas a graphite, we can get something like naturally occurring graphite ore, and then we can get large scale application. We can prepare by using this graphite type of the flakes by using the naturally occurring from the graphite ore, etc. So usually that we can try to prepare the materials, and they can do surface coating either by chemical method, especially protecting surfaces. People, they can use it a chemical and then ALD. These are all things we can nowadays. I think some industry, they are able to produce the materials in nearly tons of the quantity they can supply. So there's not a problem with preparing large scale. So already been demonstrated with the different companies in all over the world. So these are the important, I think people may see something like NCA chemistry. NCA means lithium, nickel, LNCA, LNCM means nickel, cobalt, manganese. 111 means like one third, or 62 means 60% of this nickel, 20% of cobalt, and 20% of manganese. And then 80 means 80% of nickel, 10% like, okay. Among, I think 80, 10, 10 seems to be good. Yearly will get 200 milliamps capacity. So some iron phosphate is reasonably good because although the lower potentials and is most little bit less expensive, and vanadium fluorophosphate and then manganese compounds are a little bit 4 volts material, 4.2 volts we can use. So this one example is if you want to prepare some the bulk carbon graphenotherm, this is very useful tool. Suppose you in this technique we've been prepared a lot of the oxide based lithium containing oxide we've been prepared in the laboratory. So for example, lithium iron phosphate or lithium vanadium fluorophosphate. So idea here is that if you want to reduce, for example, molybdenum 6 plus to 4 plus, if you want to reduce, so that accordingly we can use two carbon. So you calculate amount of carbon you can use, so we can reduce so molybdenum oxide. So this is the way typically. So for example, so depending on the oxides, so we need appropriate amount of carbon and then finally heat it into, for example, 650 to 850 degree, and finally we can pass the argon gas, we can get a respective oxide. So remember, sometimes people are working with catalysis or some compounds, some other applications. I think there we need some metals with the carbon matrix. So accordingly, we use appropriate amount of the carbon. So means more carbon is needed for their applications. So in some, there's one example, lithium vanadium fluorophosphate. It is a 4.2 volts cathode materials, and then it's a reasonably good thermal stability when compared to the lithium cobalt oxide, really good, and close to the lithium iron phosphate. So these are the typical XRD patterns since the triclinic structure, so that way by knowing the software we know that what type of the structures, and based on that one we can calculate the lattice parameter, etc. So once your powder is ready, so either you can in a lab scale, always you can do it a small scale, for example, 5 gram, 6 gram bags you can try to prepare. Or industry, what they will do, they exactly 5 kilo or 500 grams. Again, with respect to industry also, they will do this type of small production. Once they are very happy, they can go to scale up of, for example, kilograms quantity they can do. So usually I told you the conducting weigh 70 or 80% active material, conducting carbon and binder all mixed together and make a slurry and try to coat it on the aluminum and copper foil depending on the either cathode or anode, and then twin roll it so in order to make a good contact, and punch the cell. It depends on, for example, if it is a bigger dimension or post cell, or for example in a cylindrical cell you can do, for example, or for example if you want to use this like 16 cells, coin cell also you can do, and finally dry the things and put in the glow box to make a cell. Since you're working the organic electrolyte, you would use a glow box. Okay, so usually if you have industry, so they'll use something like dry room, so that all the everything is automated, mixing, coating and calendaring, everything. So till depending on the everything you can do. So they're all the commercially available big type of the equipments are available. So that's why, so now it's a lot of suppliers are going to supply. Only thing is that we need a large scale facilities or lab, etc. I can do prepare this type of such things. So this, for example, typical coin cell is, for example, this particular bottom cap, you can try to put material there, and then separator and lithium metal finally, or if you can use a graphite electrode and the top cap, and your cell is ready, and you can do charge discharge. For example, you can see the charge and discharge or capacity or cycle number. So if it is good materials, it almost takes 6 months we cycle the cell. So this is reasonably good. So in summary, if you want to look for any higher density, so this among the 3 type of cathodes, like iron 3.5, around 3.9, nearly 4.2. So it's a good, nice that look for the higher charge potential is really good. That is the one you can make it high energy density still. So, and also we have to get extended plateaus for the practical applications. So anyway, you can do as a researcher, depending on you can do further understanding how the like XRD, just see the how the structures are same during cycling, or impedance to see how is with cycle number, how the resistance is going to vary with cycle number, etc. So in summary, good cathodes means you get higher charge potentials, so that automatically you may get high energy density. So anyway, these are the some new vanadium based cathode materials have been worked in the literature. So these are some of our examples. Some early reports have been reported in the for the first time in the literature, something like new metal organic inorganic framework materials. So compare iron phosphate to the benchmark material 3.5 to nearly 4.1, which means that high energy density we can get. Still, so there is a small, there is further improvement in the capacity needed, although we don't claim that although voltage is really good for the practical applications, the capacity has to get higher, so that then only we can use it for the practical applications. So sometimes people may ask, we also work in sodium. First among our experience, lithium is good, followed by sodium. Again, if we talk about potassium batteries, again, so either due to the charge, we'll get something lower discharge. You know that potassium ion has a slightly higher ionic radiation due to mobility issues. Anyway, recently with further small improvement in the electrolyte combination, the people have been achieved improvement in the capacity. So these are a few examples on novel vanadium, for example, lithium vanadium fluorophosphate type of the materials. So interestingly that, so what I'm mentioning that this particular cathodes are very useful. So that's why later after first report, there is a extensive work is going on with all over the world. So it clearly shows that there's a first, then afterwards some of the new novel, including Nobel laureate, some few other groups, some USA people have been looking into the system. I think they have been further improve the performance. So what I am mentioning that it is very important, whatever the research, at least some new materials are they try to report irrespective of any journals. So that's why later some ex people, they look into your system, and then they can improve further performance. Okay, I'm going to maybe another 10-15 minutes I have. So still quickly I'll go through the So skip the details and how we are going to prepare the materials. Again, clearly I'm mentioning something like 4 volts cathode materials. So anyway, I think another example is the people are talking about the grid storage again for them. So irrespective whatever they use, the cost is a major one. So if you compare with what the environmental availability, especially lithium mining is little bit low when compared to the sodium. So again, another disadvantage is that as you can see the ionic radius keep on increasing. So as a consequence, we see that there is a problem with the mobility issues. Still, cost-wise is lower. For example, grid storage, they may consider the cost is a lower cost. That's why sodium is a little bit. Anyway, people have been focused on sodium-based system already in literature. There are also some old data in 1973. Still, few example have been already worked with different author. So the different. So this is one example. If you see the lithium containing compound, nearly 4.2 volts we can get, whereas sodium compound is 3.5. So in summary, you may get higher energy density here and lower energy. It means slight lower because as you said that lower potential we can see. So again, I think I will skip the details on the like for example, some carbon coating people have been adapted nearly around. So you can see almost like 3 point less than 3.45 or 4 volts this cathode. Again, sometimes due to carbon coating, we can improve the rate capability as well as we can check the, as you see, you can see clearly lower resistance by using the impedance studies. So again, in one quick line, people may ask you that although in battery, any electric vehicle batteries, although sodium or lithium is one component, in addition, we have to see either anodes, we do have any graphite, because I know that graphite, we cannot use it for the sodium battery because we need something like hard carbon. And another important is the RN, still the current collector, and neodymiums. They're all the things. So whichever the country they have this particular resources, I think they can reduce the further cost. I think they will monopolize the market, etc. So I think another part is the anode-based materials. Again, either you can do lithium, graphite, and then this different type of systems have been among them. Only popular is, for example, these are the few compounds. Although I'm going to discuss too many examples. So, for example, you may see the graphene. Although with graphene alone we cannot replace the graphite. So to remember. So in a practical applications, you have to get a lower discharge potential. That's why. So that is the fundamental things I already clearly mentioned them. So again, in terms of carbon-based system, they can use it for the different type of the applications. So anodes, I think these are the limits. I think sometimes people call as a nano size, nano structuring the system, or you can use from new matrix elements or something like both alloying and conversion reactions. So these are the few examples I'm going to mention. So for example, so alloy-based systems, you can see silicon, tin, and these are the alloy forming elements. So these are the expected theoretical capacity. So as of now, silicon, making nano silicon large scale is a little bit tedious process, is not straightforward. I think you have to, so it will very, in large scale is a little bit, that's why still there is interesting things going on with the different part of the companies. For example, silicon alone, the people are anode materials, people are concentrating. So in case of tin-based alloy forming elements, you can see there are a lot of oxides have been earlier reported from our group. So overall summary is that again, the voltage is almost like somewhere 0.25 to nearly 0.5 volts in case of tin containing alloy forming elements. Still the challenge is that so irreversible capacity in the first cycle would reduce. So that a little bit challenging in this particular type of the oxides. So this one example, if you go for the nano size to submicron size materials, these are new materials. So and something like nano seems to be good because reasonably good cycling stability up to 100 cycles, whereas a submicron size, you may see small capacity fading after a few cycles. Again, we checked with something like impedance and other thing complementary tool to see that how the resistance is going to be. We know that conductive matrix element like vanadium seems to be good, so that we can see the lower resistance during at the end of the almost like 100 cycles. So anyway, there's a lot of series of the other type of anode materials. A lot of oxides have been reported. The main challenge here is that although capacity is slightly higher, for the practical application, you want to make a full cell, this discharge voltage would reduce further. I think that is very important for the practical applications. So in summary, I think a lot of the, either you can do some graphene or a lot of things, people like either chemical method, people they can use some conducting carbon coating, people they can use with different type of oxide for the different applications. So either you can do some sulfide based systems. So again, some anode wise something sodium compounds are slightly lower discharge potential when compared to the lithium containing compounds. So again, another important point you have to, in case of this alloy forming element, we have to be careful. Although, so voltage, you have to be careful. Don't go to higher voltage respectively, accordingly. So each material has alloying limit. Accordingly, you have to restrict the voltage. If you go to higher voltage, you may get higher capacity is going to fade. So that's why we need optimum voltage is 1 volts or 1 or 1.2 is good for the antimony. So I think nitrites also we've been studied because the advantage of nitrogen, so 3 lithium can be used, whereas oxides only 2 lithium. It means that higher capacity we can get by using the nitrogen based system. Anyway, we try to either first attempt was to try to prepare in thin films, and now it is a bulk by using oxides passed with ammonia gas with their respective nitrites. And remember, you have to treat sample nearly low temperature, so then we can get, again, these are the capacity, almost like 800 to 900 capacity we can get. The again major challenge in this, similar to the oxide, I mentioned that voltage is the real challenge you have to reduce, then only we can use it for the practical applications. So among all type of another type of titanium, among them Li4 TuF12 is the only one people are using for your commercial EVs. So that since LTO mix with some high voltage cathodes, and they made a full cell already been demonstrated with this particular type of the cathodes. So now quickly I'll go through one example on the importance, something like some nanomaterials, use of nanomaterials, for example, energy storage. So again, I think these are one. Quickly I'll go through importance of molten salt. Usually if you take any nitrate containing lithium salt and try to put it in the titanium containing salts, put in alumina crucible, heat at various temperature, wash with water. Again, usually in case of photocatalysis or any other application, I think we need something like high surface area and particles should be nano size in it. So I think with this approach we can get, so these are typically low temperature to go to high temperature. So these are surface area nearly 200 meters square you can get by using 280 degree. High temperature, we can see the reduction of the surface area as well as the increase in the average crystallite size. In summary, if you go for nano size to submicron size, how the crystallite size, etc. So overall, so you can see something like nano size material seems to be good. So interestingly, I think already people have been covered with silicon type solar cell. Again, some of the nano size TiO2, since it is well known, DSSC people have been demonstrated. So these are one example use of the high surface area material with commercial P25. Although we can get some small improvement in the what they call as efficiency. Still recently, I think the people have been use the photo battery also. So for example, use of the sunlight. I think we can use something like people have been reversible intercalation. People have been studied by using the photo battery concept also. I'm going to skip the details. Again, importance of materials. For example, you want to use it for the gas sensors or some other type of the applications. So in summary, so what my, for example, if you have the engine, you can see the oxygen sensors for automobiles. Again, the materials will vary. These called ATS stabilized zirconia. That one is also well known. This type of sensor they're going to use. So idea here is that if you want to see the, so rich in the, for example, lean mixtures and rich mixtures, depending on the voltage, and that's the advantage of this sensor for the use of the automobile industry. So I'm going to tell some little bit some more information about the again, some materials people can use it for supercapacitor. Either you can do double layer, pseudo, etc. In fact, this is not my interest to the present topic. I'm going to skip the details. There are some materials you can use it for the electrocatalysis. I think I'll skip the details on the how the material synthesis, since my time is almost like 1:30. So quickly I'll go through. Suppose, for example, people are interested, any chemists are there, I think you, so what I'm mentioning that depending on the application, we need appropriate current collector you have to use. Accordingly, we can use, or sometimes like so organic batteries, cathodes is a little bit difficulty. Problem here is that we don't get any good energy density because the voltage was a little bit lower, and we don't see any plot potential. That's why there's a little bit drawback of this organic type of the cathodes. So for example, use of the, for example, electrospinning. These are the different type of techniques people want to study improvement in the furnace. People can study using different techniques, electrospinning or electrospinning and spraying. For example, people want to use the fuel cells or electrocatalysis. I think people want to use the fibers coated on the something like nanomaterials or metal oxides, etc. They can do. So again, for example, this is a ball milling approach. So sometimes people want to be preparing alloys. First, you have to mix all together, and to make a composite. For that case, we can use something like high energy ball milling. Either you can do vary the time and milling time, everything you can do. So idea is this is a way to mixing the to prepare some nano composite material using. So this applies to any type of this. I think this type of techniques are common for the any, for example, mechanical engineering backgrounds, but people want to use it for lightweight alloys, so they can use this particular technique. Or sometimes people use microwave synthesis, is similar to the what our kitchen microwave. It is like more specialized setup. I think you want to use sulfides, oxides. I think with a less duration, we can do mixing easily, and then we can do interesting oxides by using this approach. I think one example is something like for gas separation, the people they want to be something like in nanoparticles, or for example, they need something like porous material. So for example, so any purification of oxygen or any type of the gases, I think we need a proper catalyst. So that for that case, so we need a size specific materials, and then that's why we have to use it. Depending on application, we need appropriate things. So quickly, I'll go through one last few slides. I think what are the failure mechanisms, either by using any battery arises due to the either mechanical abuse, electrical abuse, and thermal abuse, or what they call thermal runaway, and then dendritic growth, etc. So again, you may, so what I'm mentioning that there is safety, already I mentioned that. So one example with in situ techniques, it will tell the, so for example, these are real, when the battery is running. So these, for example, cathode, anode, everything put together in a beryllium window. You can see, you can monitor this one, for example. So we can see the charge and discharge. We'll see what is going to happening with real time. We see the X-ray patterns. So what I'm mentioning, in case you are, for example, any supplier, they'll mention to cut off voltage at 4.2 or 4.3, try to restrict that to a particular voltage. Don't exceed to higher voltage. Although if you go to higher voltage, you may get slightly higher capacity. There is a problem with the safety, oxygen evolution. For example, this one particular cathode, if you remove too much lithium, you can see lower angle shift towards the lower to theta, in the sense that there is a volume expansion, and also lattice parameter. We can see the difference in lattice parameter as a consequence. Due to slow charge discharge cycling, we can see the, so it is a nice safer way that anything they mention that we have to follow the safety limit accordingly. We have to cycle the battery. Anyway, we can do something like fancy technique, neutron, and in situ techniques, etc. So what is another things we like, for example, another techniques we can do. So again, I think 2 slides I'm going to ending my presentation saying that whatever research we do, it is applies to including solar or any type of research. Again, sustainability is very important. So for example, any batteries you must to recycle. So that's why, so either these are the almost like forecasted one is almost like 11 million metric tons of the spent batteries discarded in 2030. In the sense that our job is to, so it may use to a lot of problems, like ecotoxicity and the global warming. So it is very important to we have to recycle the material in a proper way. That's why I think we have to educate them. So we cannot, for example, these are the flammable example electrolytes are there. We cannot treat it, maybe fire retard. So as a consequence, like nitrogen oxide of like a gas evolution and HF, etc. This is not really good. Okay, so it's very important to do properly to recycle it. Either you can do direct, or sometimes people are thinking about this battery for secondary applications, for example, household applications, okay, etc. People are thinking. So usual way is that you discharge the battery again and dismantling and pre-treatment. Either you can do separation cleaning or mechanical separation or chemical separation. You can do the hydro and pyrometallurgy approach. So remember, if it is a lithium cobalt oxide, you will not get lithium metal exactly. You can get some lithium carbonate. So for example, lithium cobalt oxide mixed with carbon, you'll get a lithium carbonate plus cobalt metal. So that's why, so if your 2-3 elements are there, the cost is going to vary depending on the this particular technology, etc. So these are my small conclusions. So in summary, I think these are multidisciplinary areas. What are the things for energy density and longer series, cost material, and always you to look into the, I think cooperation between scientist and engineer is needed. Whatever the research you do, I think that is very important for the like our practical applications. So again, thank you very much. Maybe I may take some question and answer. I think that will be better. So if you have any questions.
Yes, sir. In chat box, it was there. What is semiconductor or chip storage in EV nowadays?
Okay. So 1 minute. Just I didn't see. Okay, chat box. Okay. So I don't know, like usually semiconductor is the word is semiconductor, you know, that metals insulator semiconductor. For example, that is the one. I don't chip storage in EV nowadays. It means I don't. This is not so clear for me. Maybe chip storage in the sense that, for example, so it depends. People are talking about this small cell, for example, you know, like so it's like micro battery, like layer by layer, they can put it. That is called as a small, like thin film micro battery type of this one. I don't know. This is really applies to this one because you know that whatever the energy density is coming with this too small when compared to the this one, you know. So maybe if you discuss more, then I'm able to explain, you know, so this particular thing. Okay, so. Please inform that whatever nanotechnology used in the, okay, so usually for example Tata, so this particular usually what is the technology they used. So the mainly as of now presently we have two like materials. We know that NCM, the standard metal nickel, cobalt, and there is layer type of cathode is a common one, and negative side they use the graphite and the electrolyte like that way. So the materials are same. So usually sometimes, you know, these trade secrets are slightly vary because each, you know, this auto industry is a lot of competition. Is not whatever the patents, it is slightly different when compared to the trade secrets, you know. So sometimes, so we know as of material point of view, they stick to the layer type of cathodes, and then electrolyte they used. Okay, so sometimes some people they use something like to avoid the flammability issues. They use something like additives. You know, we can reduce the what they call safety issues. People they can use and some cases we use something polymer electrolytes also. So people are using. Okay, so maybe this one I can, if you are anybody is interested, they can send me more details. I think I can answer more on chip storage in EV. Okay, so. So probably he is asking maybe if people are in the electronic engineers, maybe usually for the EV storage, I think they may need something like silicon nitride technology. For that case, maybe if they're talking about that one, I'm not sure. Okay, so I think they need something like silicon nitride materials for that one. Okay.
Dear participants, please switch on your video. We will take another snapshots. Anything you want required regarding this session, please, SAR is already available. Please make us. Someone, someone has raised a hand. Mandal, you raised hand. What is your, any query is required? Before that, please make switch on your video, please. All participants, total 88 members are there. Please, number of participants are more. We can take some snapshots, please. And meanwhile, anything we required regarding this session, queries or anything we have clarification is required. star is all available, please. Sir, how reliable are the EIS study of for batteries?
So I don't know. As of now, reliability is based on my experience. So EAS is a little bit really good technique. So without advantage of this, what they call impedance spectroscopy is that just you can use particular lead and then you can put give the connection without opening and you can tell the. So if you want tell reliability is 100%, don't. So at least usually that you have to see how much capacity is going to happen. I think this is like complementary tool. So advantage of this technique is that without opening the like individual part and you can tell clearly, okay, so suppose some battery is working very well, or sometimes, I know some batteries are like fast charging. You can finish within few minutes, means something wrong with connection. So you can put the ES like positive negative terminal. You can see something like a lot of noise is there. It is something problem with the connection. So that way, so this technique is very useful, and that is my personal opinion. In fact, so that one only my suggestion is that you keep on doing the experiment and then you will get some idea, that is my personal, okay. So I think this is a very standard technique people are using for including solar cells or electronic engineers, people, they want to see the circuits. I think this is very the standard way people can use. And also it may be slightly expensive too, because high frequency analyzer, it is costing, sometimes you go to high frequency, the cost will be slightly higher, yeah. Okay, what is it? Okay, yeah, people are talking about the battery recycling method. So usually, so I didn't, since I have another 2 more slides are there, I didn't, maybe people are interested, I can, usually people, hydro and pyrometallurgy is one. So that this technology has been already demonstrated by Umicore, that is a big chemical industry. So this, what they're telling that use this particular technology is like cost lesser expensive when compared to the what they call a pyro, means a water-based system, because the chemical methods is a lot of leaching. Water you have to recycle it again. The water is a problem again. The effluent treatment you have to do again. Cost is going to be increasing. That's why people, they think that like pyrometallurgy approach is that is good. And direct method, direct recycling is a little bit difficult. Means open the battery again, filling the electrolyte. People are trying to do. The results scholars put some additional lithium source and do. But that is called a direct recycling method. Okay, and calculate the battery efficiency is nothing but if you talk about the Coulombic efficiency, already I mentioned that you have to see the how much charge capacity minus charge into discharge capacity can do, like 100 minutes, that way you can calculate. And if you talk about the capacity fading, it is nothing but, for example, what is the value you are getting from second cycle or n cycle is something, if it is fading, so value keep on this is a way, standard way people can do. I think that way we can, so whatever the value you're getting from the amp hour in particular, for example, before like 1 month, or if it is after about 2 months, you get some same amp hour you will get, then it clearly indicate that it is efficiency is good like that. Or sometimes you keep on reducing, means something slowly your battery is going to die like that way. Okay, so these are the things.
Okay, thank you, sir. Thank you.
Thank you.
Any participants regarding you required another 5 minutes? Then. What was the time now, sir, in Canada? M.V.Reddy, sir?
Yeah, it's almost 1 hour 20 minutes. Yeah, early morning. Yeah.
Very good. Okay, sir. Participants are okay, sir. Once again, thank you, sir, for accepting and making to deliver very interesting topic on this energy storage materials. Once again, I am very heartfully thank you, sir. Thank you, sir. Once again.
Okay, thank you very much. Okay, thank you. Okay, have a nice for you is
Yes.
afternoon. Okay, okay, thank
Thank
you.
you.
Thank you very
Okay.
much.
Fine, sir.
Thank you, thank you.
Okay, participants, thank you. Again, the session